Right now, at this exact moment, there is a machine traveling through the freezing, silent dark of interstellar space, carrying a working instrument that its more famous twin lost before most of the people working on the mission today were even born. We are told, almost universally, that Voyager 1 is the pioneer of the interstellar frontier. It is the farthest human-made object in existence, the one that crossed the threshold of our solar system first, the one that captured the imagination of the world with the pale blue dot and the golden record. But there is a quiet, profoundly important truth that planetary scientists and deep space engineers discuss only in hushed, reverent tones. Voyager 1 went into the interstellar medium blind to the very thing that defines it. Its plasma science instrument, the only tool designed to directly feel the wind of the stars and measure the temperature of the space between them, died in 1980, 4 decades before it ever reached the edge. Voyager 2, trailing behind in a completely different direction, carrying a functioning plasma sensor, did what Voyager 1 never could. It did not merely cross the boundary of our star system. It felt it, it measured it, and what it found when it stepped into the cosmic ocean did not just complete the picture Voyager 1 had sketched in the dark. It shattered our models, rewrote our understanding of how our sun interacts with the galaxy, and revealed that the edge of our solar system is not a clean, frozen wall, but a violent, leaking, dynamic coastline that defies every law of physics we had written to predict it. To truly understand what Voyager 2 achieved, and why its journey has rewritten the textbooks of astrophysics, we must first look at the profound asymmetry of their paths. The year was 1977. The alignment of the outer planets was a rare celestial coincidence that occurs only once every 176 years, offering a once-in-a-lifetime opportunity to use the gravity of Jupiter and Saturn to sling spacecraft all the way to the edge of the solar system. Voyager 1 was launched on a fast, aggressive trajectory. It was designed to sweep past Jupiter and Saturn, sacrifice any hope of visiting the outermost planets, and make a close, high-stakes flyby of Saturn's massive, shrouded moon, Titan. This trajectory bent its path sharply upward, throwing it out of the ecliptic plane of the planets and setting it on a rapid, direct course toward interstellar space. It was a sprint. Voyager 2, however, was built for the marathon. It was sent on a slower, infinitely more complex path, a cosmic billiard shot that would require it to visit all 4 of the gas and ice giants. For nearly half a century, Voyager 2 has stood as the only machine constructed by human hands to have visited Uranus and Neptune. It is a distinction that remains unmatched, a testament to an era of engineering that worked with computers containing less memory than a modern car key, yet managed to navigate across billions of miles of empty space with near-perfect precision. When Voyager 2 swept past Uranus in January of 1986, it revealed a world that seemed to actively mock the neat, orderly rules of planetary formation. Uranus was not merely tilted. It was lying on its side, its rotational axis inclined by an astonishing 97.77 degrees, likely the result of a cataclysmic collision with an Earth-sized protoplanet during the infancy of the solar system. Because of this extreme tilt, Voyager 2 found a magnetic field that was unlike anything scientists had ever observed. Instead of being aligned with the planet's rotation, the magnetic field of Uranus was tilted at a bizarre 60-degree angle and offset from the planet's center by 1/3 of its radius. The spacecraft watched as the planet's magnetosphere tumbled through space like a lopsided spinning top, creating a chaotic, corkscrewing magnetic tail that baffled theorists. It discovered 10 previously unknown moons, mapped 2 new, faint rings, and returned the first close-up images of Miranda, a moon that looked as though it had been violently shattered into pieces and then clumsily reassembled by gravity, leaving giant, towering ice cliffs that plunge miles into the vacuum. 3 years later, in August of 1989, Voyager 2 made its final planetary encounter, screaming past the blue, wind-swept disk of Neptune. Here, at the very edge of the Sun's planetary family, where the solar energy is 900 times weaker than it is on Earth, scientists expected to find a quiet, frozen, geologically dead world. Instead, Voyager 2 found a dynamic, raging atmosphere, whipped by supersonic winds reaching speeds of over 2,400 kilometers per hour, the fastest winds ever recorded in the solar system. It photographed the Great Dark Spot, a massive storm the size of the Earth that has since vanished, and discovered 6 new moons, including the blocky, heavily cratered Proteus. But it was Neptune's giant moon, Triton, that provided the most stunning revelation of the flyby. Voyager 2 captured images of active cryovolcanism, nitrogen geysers erupting from beneath the frozen crust and shooting dark, carbonaceous dust 8 kilometers into the razor-thin atmosphere. Triton's retrograde orbit and its striking resemblance to Pluto led scientists to realize it was not a native moon of Neptune, but a captured Kuiper Belt object, pulled from the dark outer reaches of space and locked into a slow, circularizing death spiral around the planet. These discoveries were monumental, but they came at a cost. Every planetary encounter, every gravitational assist that bent Voyager 2's trajectory toward the next target, delayed its progress toward the interstellar boundary. While Voyager 1 had cleared the ecliptic plane and was screaming toward the Heliopause at a speed of 38,000 miles per hour, Voyager 2 was left to climb out of the Sun's gravity well at a more measured pace of 34,000 miles per hour. By the time Voyager 1 crossed into interstellar space in August of 2012, Voyager 2 was still more than 3 billion miles behind, still climbing through the outermost region of the Sun's domain, the Helios Heath. For 6 years, the scientific community celebrated Voyager 1's entry into the galaxy. But behind the headlines there was a quiet frustration. Voyager 1 was sending back data that was deeply confusing. It was detecting changes in cosmic rays and magnetic field lines, but it could not tell scientists what the plasma, the superheated, ionized gas that fills the universe, was actually doing. To understand why this was such a devastating limitation, one must understand what plasma is and why it holds the key to the boundary of our star. The solar system is not just a collection of rocky planets and gas giants orbiting a ball of fire. It is a giant protective bubble carved out of the interstellar medium by the Sun itself. This bubble is called the heliosphere. The Sun is constantly boiling off its outer atmosphere, launching a torrential stream of charged particles, protons and electrons moving at speeds of up to 1 million miles per hour, outward in all directions. This is the solar wind. This wind is a hot, highly ionized plasma, and as it rushes outward, it carries the Sun's magnetic field along with it. But the space between the stars is not empty. It is filled with the interstellar medium, a cold, dense plasma made of the remnants of ancient supernova explosions and the stellar winds of neighboring stars. The point where the pressure of the outbound solar wind perfectly balances the pressure of the inbound interstellar medium is the heliopause. It is the ultimate boundary of our solar system, the place where the Sun's dominion ends and the domain of the galaxy begins. Because plasma consists of charged particles, it is intimately bound to magnetic fields. The solar plasma and the interstellar plasma cannot easily mix. They act like oil and water, pushing against each other, creating a distinct interface. If you want to know when a spacecraft has crossed this interface, you must measure the plasma. You must measure its density, which should spike dramatically when you leave the diffuse solar bubble and enter the cold, compressed interstellar medium. You must measure its temperature, which should plunge from the millions of degrees of the solar wind to the tens of thousands of degrees of interstellar space. And you must measure its velocity, watching as the outbound solar wind slows to a crawl, turns sideways, and is swept away by the cosmic current. But when Voyager 1 crossed this boundary in 2012, its plasma science instrument was dead. The failure of Voyager 1's plasma science instrument in 1980 was a mechanical tragedy of the highest order. The instrument, designed to catch charged particles in a series of electrostatic cups and read their electrical currents, had suffered a gradual terminal loss of power and sensitivity during its outbound journey past Saturn. Without it, Voyager 1 was effectively numb to the wind. When it crossed the Heliopause, it could not feel the shift in plasma density or the drop in temperature. It could only infer that it had crossed because its plasma wave subsystem, an instrument that measures waves propagating through the plasma rather than the plasma itself, detected a sudden vibration triggered by a solar flare that rattled the surrounding space like a bell. It was an indirect, fleeting measurement, a single data point in a vast, unknown wilderness. It was like trying to determine the temperature of a room by listening to the hum of the air conditioner. This is why the scientific community waited with bated breath for Voyager 2. Its plasma science instrument was not just working, it was highly sensitive, still functioning after 41 years of exposure to the brutal, freezing vacuum of deep space. On November 5, 2018, at a distance of 119 astronomical units from the Sun, Voyager 2 finally reached the Heliopause. It was traveling southward, heading toward a completely different region of the boundary than Voyager 1, which had departed to the north. And as Voyager 2 crossed that invisible threshold, its functioning plasma sensor did something that had never been done before in the history of human exploration. It recorded the transition directly, second by second, particle by particle, capturing the raw physical state of the boundary between a star and the cosmos. When the data from Voyager 2 was compiled and published in 5 historic papers in Nature Astronomy in late 2019, the results sent shockwaves through the scientific community. The models that astrophysicists had spent decades building, models based on fluid dynamics, magnetic pressure, and Voyager 1's incomplete data, were not just slightly off, they were fundamentally wrong. The first and most shocking discovery was the sheer structure of the boundary itself. Scientists had envisioned the Heliopause as a relatively clean, sharp transition zone, a neat line where the solar wind simply ran out of steam and gave way to the interstellar medium. Voyager 2 revealed that the Heliopause is not a wall. It is a complex, turbulent, 100 million mile wide transition region. As Voyager 2 approached the boundary, its plasma instrument recorded a bizarre phenomenon. Instead of the solar wind smoothly flowing outward and then turning aside, it found a region where the solar wind had slowed to a near-complete standstill, but remained hot. Then, as it crossed the actual Heliopause, the density of the plasma did not just rise, it surged. The interstellar plasma was 40 times denser than the plasma inside the heliosphere, confirming that the space between the stars is a thick, cold soup of particles. But what truly confounded scientists was that Voyager 2 detected a massive, hot, compressed layer of interstellar plasma sitting just outside the boundary. This was a boundary layer that no model had predicted, a region where interstellar particles are actively piling up against the heliosphere like water building up in front of the bow of a moving ship. But the most beautiful and unsettling discovery made by Voyager 2 was that the Heliopause is leaky. For decades, it was assumed that the solar wind and the interstellar medium were kept strictly apart by their respective magnetic fields. Voyager 2 proved otherwise. Its low-energy charged particle instrument and its plasma sensor detected a continuous, reciprocal exchange of material across the boundary. It found tendrils of interstellar particles punching inward through the Heliopause, traveling hundreds of millions of miles into the solar system like roots growing through concrete. Even more surprisingly, it detected a stream of solar particles escaping outward, leaking into interstellar space and forming a thin, hot halo around the exterior of our solar bubble. The heliopause is not a barrier. It is a membrane, a porous coastline where two cosmic oceans crash together, mixing and spraying across the border in ways that challenge our most basic understanding of magnetohydrodynamics. The temperature data returned by Voyager 2's working plasma instrument was equally revolutionary. For years, scientists had estimated the temperature of the local interstellar medium based on light absorption from distant stars and theoretical calculations. They believed the local interstellar cloud was relatively warm, perhaps 6,000 to 8,000 degrees Kelvin. But when Voyager 2 took the first direct, in situ temperature measurements of the interstellar plasma, it recorded temperatures between 30,000 and 50,000 degrees Kelvin. This was an order of magnitude hotter than predicted. This extreme temperature is not hot in the sense of heat that would melt metal, because the density of the particles is so low that there is almost no heat transfer. Instead, it means the particles are moving with incredible, unexpected kinetic energy. The interstellar space surrounding our solar system is a highly energetic, dynamic environment, shaped by magnetic pressures and cosmic ray winds that we are only beginning to comprehend. This temperature discrepancy raised a profound, troubling question. If the interstellar medium is this hot and energetic, why is the heliosphere as large as it is? The size of our solar bubble is determined by the balance of pressures. If the external pressure of the interstellar medium is higher and hotter than we thought, the heliopause should be pushed inward, compressing our solar system. Yet, both Voyager 1 and Voyager 2 crossed the heliopause at almost exactly the same distance from the Sun. Voyager 1 at 121.6 astronomical units, and Voyager 2 at 119 astronomical units. This symmetry is itself a profound mystery. Voyager 1 crossed during solar maximum, when the Sun's activity was at its peak, and the solar wind was pumping out massive amounts of energy, which should have pushed the boundary far outward. Voyager 2 crossed 6 years later, during solar minimum, when the Sun was quiet and its wind was weak, which should have caused the heliosphere to contract significantly. Yet, the boundary had barely moved. This observation led Ed Stone, the legendary Voyager project scientist who guided the mission from its inception in the 1970s until his retirement in 2022, to conclude that there is some unknown, stabilizing force at play at the edge of our solar system. There is a mechanism, perhaps related to the alignment of the local interstellar magnetic field, that acts as a buffer, preventing the heliosphere from breathing in and out with the solar cycle as we assumed it would. We do not understand what this force is. We do not know if it is a local anomaly of our current position in the Milky Way, or if it is a universal law governing all astrospheres across the galaxy. The data from Voyager 2's plasma instrument did not just fill a gap in our knowledge. It revealed a massive, gaping hole in our understanding of basic stellar physics. As we stand in the summer of 2026, the urgency of this science has reached a fever pitch. We are witnessing the final agonizing chapters of the Voyager mission. These two spacecraft, built in an era when slide rules were still common and computer code was written on physical punch cards, have survived for 49 years in the most hostile environment imaginable. But they are running out of time, and they are running out of power. The hearts of these machines are their radioisotope thermoelectric generators, or RTGs. These generators do not rely on solar panels, which became useless long before the probes cleared the orbit of Uranus. Instead, they produce electricity from the heat generated by the natural radioactive decay of plutonium-238. But plutonium-238 has a half-life of 87.7 years. Every single day, the fuel inside the Voyagers decays, and the amount of heat it produces shrinks. Combined with the gradual degradation of the thermocouples that convert that heat into electricity, each spacecraft is losing approximately 4 watts of power every year. At launch, they each had access to 470 watts of electrical power. Today, that number has dwindled to less than 230 watts, barely enough to run a few household light bulbs. For decades, the engineering team at the Jet Propulsion Laboratory has managed this power decline with unparalleled brilliance. They have turned off heaters, leaving the spacecraft's instruments to freeze at temperatures far below their design specifications. Yet they have somehow kept working. They have disabled non-essential systems, shut down the planetary cameras, and squeezed every milliwatt of power out of the aging platforms. But we have reached the absolute limit. On Voyager 1, the power budget has become so critically low that in April of 2026, engineers were forced to make the painful decision to shut down the low-energy charged particle instrument, one of its last remaining links to the interstellar environment. Voyager 2, because of its slightly different operational history and trajectory, has slightly more power headroom, allowing it to keep 3 science instruments running: the magnetometer, the plasma wave subsystem, and its crown jewel, the plasma science instrument. But this margin is vanishingly small. If nothing is done, Voyager 2 will be forced to shut down its plasma sensor within the next 12 months, silencing the only direct voice we have in the interstellar medium. To prevent